Welcome to the William M. Starkle Planetarium. So glad you could join us this evening. So on the first Friday of every month during the school year, we always host a lecturer who speaks about the scientific field that they work in. Sometimes it's a researcher, sometimes it's an enthusiast of that sort, and they just love to share that world of science. We've been calling this for several years the James Kaler Science Lecture Series in honor of Jim Kaler, who gave lectures here for about 30 years straight. Always in the realm of astronomy or astronomy-related fields. So our speaker tonight is Professor Nicola Perry, and she comes to us from the University of Illinois. I believe it's the Department of Materials Science and Engineering. She earned her bachelor's degrees in materials science and engineering as well as in French studies at Rice University. Then she went and earned her PhD in material science and engineering. I always have to say that so fast, excuse me. At Northwestern. She followed that up with some postdocs at Northwestern, at MIT, and also at Kyushu University. She was actually on the faculty there as part of the International Institute for Carbon Neutral Energy Research. Okay? So she's going to talk to you folks about some solid-state ionics. It's a novel class of ceramics, and I cannot say many more words than that before I just start sounding like I'm giving gibberish because I don't know what I'm talking about. But I'm going to leave it to the award-winning researcher here, Dr. Perry, to tell you folks more about these ceramics that breathe.
Great. Well, good evening to all of you. It's really nice to see all of you here and giving up time on your Friday evening to come and listen to my research talk. I am going to be talking about materials development for sustainable energy and specifically ceramics. That's the area that my group does research in on campus. And I'm coming from this Department of Materials and Science and Engineering, as you heard in the intro. And so I just wanted to mention, for those of you who may not be familiar with what that field is, a little bit about what that does, just to begin with. So what we do in our department is really interdisciplinary, actually. We're combining chemistry and physics and biology and engineering and trying to understand the things around us. What are they made of? Why do they behave the way they do? Why is this, white? Why is this black? Why does this bounce? Why does this break when I drop it? And we try to design new materials that will have really interesting new functionalities or solve critical problems that are facing the world. And so one class of those materials is ceramics. But if we think, back through history, one way of defining even historical ages has been through materials, right? The materials around us that we use have an enormous impact on our daily lives and the way we live. So we can think about the Stone Age, the Iron Age, the Bronze Age. I don't know what age we would think about calling now. Some people might call it the Silicon Age because that's in all of our electronic devices. But you may have other ideas as well. I don't know. But I'm going to talk about ceramics because they play a really critical role in energy. So I want to start with maybe a little bit of a silly question to provoke some thought. And the question is, what do ceramics have to do with global warming? Okay, that may not be a connection that you normally think about. And the other question is, what do ceramics have to do with a journey through the Earth? Okay, we're in a planetarium, and this is the closest I'm going to come to thinking about things that might normally take place in this kind of building, right? So we've got all these question marks here. These are some ceramic samples that we make in our lab. We make pretty small scale things. That's what they look like. So I mentioned that we're in material science and engineering. The long name of that department is intentional. There's different meanings that come from each of those terms. So I talked about materials. The science side of this, scientists are explorers. Okay, so that's going to give us a little bit of this link, right? You can imagine being an explorer, drilling down to the center of the Earth, journeying to see what's present. On the other hand, we're engineers, and engineers are problem solvers, right? So we're looking at what are these global issues that we need to tackle, and how can we take our creativity, our understanding, and our work and try and address some of those, right, and improve quality of life. So that gets at this other question. But we're going to start with a journey through the Earth, and we're going to start with the Earth's crust. So when you think of ceramics, I wonder what images come to mind for you, right? It may be plates and bowls or mugs that you have in your house. It may be the bricks that your house is built of, or it may be more artistic or functional or decorative pottery. If we look at the word ceramics and think about where it came from, most consensus is that it comes from this Greek word, keramos. Sounds kind of similar. And that means potter's earth or pottery or clay, traditionally. And so it has to do with anything that could be made from the earth, right? From the materials that are readily available in the Earth's crust. And so pots like this, would be made from whatever was most abundant and easy to work with in the ground. Okay, and so we're making ceramics from the elements that are available to us in the Earth's crust, in the ground, in the clay. And this is an image here. It's coming from the USGS. And it shows on the y-axis here, I have to apologize. I'm going to use a lot of plots. Okay, I'm working in science. We love plots and we love data, so I'm going to have to show them. So on the y-axis here, we've got the abundance of atoms of each element. It's normalized to silicon. And this is on a logarithmic scale. So each of these ticks that you go up, you're multiplying by 10. Okay, and then this is the weight or the atomic number of the atom. So the weight is increasing as we go from left to right on here. And so we see, if we look at the top here, these are the elements that are the most abundant in the Earth's crust. So we see things like oxygen, silicon, aluminum showing up. And so when people think of ceramics, they're normally thinking of pottery and ceramic ware that is coming from those most abundant elements. That makes sense that those would show up in the clay that people were working with. And so traditional ceramics are often called aluminosilicates, right? Made of aluminum, silicon, and oxygen. But my area of research and what the broader field of ceramics these days is working on is expanding beyond just what we might dig up in our garden and thinking about actually some of these other elements as well. Okay, so we actually have quite a lot to work with just in the surface of the Earth. And so sometimes I like to think of an artist has an artist palette, right? They've got all the colors that they can paint with to make their works of art. As ceramists, our palette is the periodic table of the elements, okay? And so we can pick and choose from this and combine elements together to make really interesting materials that might have properties we've never explored, or we might be designing materials for a specific targeted property. And so one way to define a ceramic actually is by its composition, by which elements are in it. And so what you would need typically is at least one element from this top right-hand corner. Those are the non-metallic elements. And often we're going to mix it with something from this big left-hand side of the periodic table, which are the metallic elements. You mix those together, and so that would give you something like an inorganic, non-metallic solid, and that's one way that people would define ceramics. Okay, so we're playing around with the periodic table and combining things from both sides. What about the structures? Okay, so I've said a little bit about the composition. So ceramic structures are usually thought of as ordered arrays of repeating structural motifs. Okay, so it's not just that we have certain elements that we're choosing in certain ratios, but they're going to be arrayed in these really interesting and quite beautiful patterns. This is just an example of a handful, but there's really a lot out there that I could have shown. And so what you can take is a small motif. Material scientists call that a unit cell. And then that is going to repeat itself through space. So imagine if you took a stamp, right? You dipped it in the ink, and you stamp it out on paper, next to each other, and you repeat that motif around. And so that's what these 3D ceramic structures are like. You can also have glasses, right? Glasses are very, very close to ceramics. And did you have a question?
Yeah, let's go
Sorry,
ahead.
I just keep talking.
You're doing
go
fine.
ahead.
What are the tiny balls?
Oh, great question. Thank you. I should have mentioned that. The tiny balls are atoms. Okay, so each of these little circles would be a different kind of atom. Usually the color means it's one kind. So here's an example of magnesium oxide. And here are the red circles. These are oxygen atoms. And the yellow circles are magnesium atoms. Does that answer your question? That's a fantastic question. Thank you. I meant to say that and I forgot. So that's great. Okay, I'll keep going. So aside from these kind of ordered structures, we also have the disordered structures. These are the glasses. Okay, they go hand in hand with ceramics. And they're also called amorphous structures. Okay, so you can have things that are ordered, things that are disordered in this family. But lots of really amazing variety in what can be present. Now, another thing to mention about ceramic structure that's very, very important is the fact that they're going to have defects in them. So I just told you, right, that these structures are these perfectly ordered arrays where the elements have their places and that repeats through space. Okay, in practice, that doesn't happen. We have defects. Defects can be all kinds of things, but it would include, for example, a missing atom, right? You're supposed to have an atom there, but it's gone. That would be called a vacancy. You can have atoms that have squeezed into a site that you wouldn't normally have one. We give them a fancy name, interstitials, don't worry about it. And there's all other kinds of defects, like atoms switch sites, or you've introduced something that wouldn't normally be in there. And those are actually key to how these materials behave. So we spend a lot of time thinking about these defects. Some examples of technical ceramics that actually depend on their defects to give them their properties and performance are shown here. So top left, we've got superconductors. One really cool thing about superconducting ceramics is if you cool them down, they become superconducting. You can float magnets above them. They levitate magnets. Pretty cool. It's the origin of maglev trains, how those work. Ceramics are used in electronics, lots of different circuit components, switches, capacitors, resistors. Those are often ceramics. Optical ceramics, so night vision goggles. Those depend on technical ceramics. So being able to see thermal imaging instead of through visible light. Audio pickups, so picking up vibrations from a guitar and turning that into an electronic signal that could be amplified through a speaker or a microphone. Those are ceramics. We have gas sensors. This is an automotive gas sensor that is in any kind of car that is running conventional combustion engine. It helps figure out what's your oxygen to fuel ratio so that that can be kept in the value it should be. And then this interesting class called superionics. This is what my group is interested in, or one of the things we're interested in. Those play a role. This is an image of a fuel cell, and we'll talk about those a little bit. Those are materials that can make ions move through them really, really quickly, and it's critical for energy applications. So I did promise we'd take a journey through the Earth. We're going to jump a little bit, though. We started at the crust. We want to go all the way down to the core in the center. And the reason I mention this is that this is something that popped up in my news feeds a lot this week. It was showing up in a bunch of different news agencies. And it's this idea of what actually is at the core of the Earth. No one has been able to dig all the way down and journey there to really see that. I mean, we couldn't. It's too hot and the pressures are too much for us. But if we could, that would be cool. So there's this paper that came out in Nature this week from another group, and they are suggesting that the core of the Earth might actually be one of these super ionic materials. And I thought that was really cool, because that's what we work on. And so the core, people have said, well, it's probably iron, right? But what people are saying now is, well, it's not just iron, but there's light elements in there as well. It's going in the direction of becoming a ceramic, right? We're mixing things from those two sides of the periodic table. So the iron is like a solid, okay? But these light elements are more like a liquid in this structure. These light elements can zip through it and move and flow through it. And that's kind of what a supraionic material is. It lets these ions become almost like a liquid, and they can flow through the material. So I thought that was cool that might be actually at the middle of our Earth. Okay, second question. What does ceramics have to do with global warming? Okay, so now we're going to put on our engineer hat, think about problem solving. So by the way, this is just an image from NOAA on land and ocean temperature percentiles for 2021 compared to the normal baseline. Breaking records in a lot of places. Red means it's a lot warmer. And this temperature rise that we're seeing is certainly correlated to the amount of greenhouse gases, like CO2, in the atmosphere. So these images on the right are coming from NASA and NOAA. They've got this fantastic site if you're interested in just looking at the latest data on climate and climate change. This is this website, climate.nasa.gov, and then these extra bits. And so they're collecting data all the time, right, on the CO2 in the environment, carbon dioxide, and the temperature change, temperatures of the oceans, et cetera. And so here's our CO2 plot. It's spiking. Here's our current level. I checked today, we're at 418 parts per million, which is way higher than it has been. It's just shooting up. These are just images of the distribution of that they can measure more recently, even just in last decade and a half or so. It's really increasing. So these are correlated. CO2 is going up. And ceramics can actually play a role in maybe helping us lower those CO2 emissions. So why is the CO2, increasing so much? A lot of it has to do with burning fossil fuels. I think most of you know this. This plot on the left is coming from the US EPA, and it's a little bit hard to read, but it's showing the total US greenhouse gas emissions. This is 2019 because they got the data for that, by economic sector. And with the exception here of agriculture at about 10%, everything else, transportation, electricity, industry, commercial and residential, most of those CO2 emissions are coming from burning fossil fuels either for heat or energy or electricity. And fossil fuels, have a lot of great things about them. They're really energy dense. And we can burn them and we can do work with that, right? So this is a heat engine diagram. You can burn a fossil fuel and turn that heat into work. You can maybe use the pressure from it to drive pistons, right? Rotate something, drive a motor. But there's a limitation on how efficient that's ever going to be. Okay, and so there's something called the second law of thermodynamics. And one of the things it says is you can never fully convert heat into work. And the efficiency of a heat engine by this law is shown here. It's related to how hot you run it. Okay, so this is the hot side of the heat engine, the cold side of the heat engine, that temperature difference relative to the hot temperature. So the hotter you run it, the more efficient it gets. But for most applications, let's think about a steam engine operating at the boiling temperature of water. It's only 21% efficient. And even the best power plants now are maybe at 33%. So it's a relatively inefficient process to get energy from burning fossil fuels. On top of that, they're emitting CO2, right, when you do it. This is just kind of a generic equation showing that process of burning a hydrocarbon in oxygen. It makes CO2. So you're getting quite a lot of CO2 emitted for the amount of energy or work that you're getting out. So what are our cleaner alternatives, right? Engineers should be creative. We should be figuring out better ways to do this, and there are better ways to do it. And one of these is through something called electrochemistry. And electrochemistry is going to include things like fuel cells that I'll talk about, electrolysis cells, which make green fuels. Things like batteries would fit into electrochemistry. So the whole idea of electrochemistry is really connecting chemistry with electrons, connecting chemical work and electrical work, and converting between those efficiently. Yeah, there's a question.
Would that also include solar cells?
It's a good question. So for solar cells, you're really converting between sunlight and electricity. And you're doing that by the light hits the material, and it separates positive and negative charges that then create electricity. You're not really changing the chemistry. So I would say conventionally, a solar cell, it's a renewable energy form. It uses ceramics, but I would probably not classify that as electrochemistry.
But can ceramics change the efficiency?
Yes, absolutely. So I'm not going to talk about it today, but a lot of ceramics are, things that I would classify as ceramics are being developed for more and more efficient solar cells. They're getting up beyond 25% efficient there at the moment with some new designs. Does that answer your question? Yeah. Okay. So with electrochemistry, at least, which is one of our options, solar is another. So there's applications that combine solar with electrochemistry as well, which are really cool. Basically, you have a different way of calculating efficiency. It depends on the energy of the chemical reaction and the heat of the chemical reaction. And so we can take a chemical reaction that would like to happen, and we can get electricity from that. We can also use electricity to force a chemical process that would not like to happen. So I'll show a couple of examples of these, but essentially these are not limited in the same way that heat engines are. We can get much higher efficiencies, so we get lower CO2 output. And in addition, we can actually do this in some cases with no CO2 emissions. Let me show some examples to make this a bit more concrete. So this is something called a solid oxide electrolysis cell. It's a diagram of it. And this is a device. It's an electrochemical device where you're going to take electricity and use it to make something happen that would not normally happen. Okay, so in this case, we're using electricity to split water. Okay, and the reason that people want to do that is that hydrogen is a fuel and it can be used later. So this is one way of storing electricity from renewable resources. So it could include solar cells. It could include wind energy. That electricity is not available all day, right? It's not available every time. It's intermittent. We want to store it. So we could use it to run one of these devices and store that energy as a chemical fuel. Here's another device. Looks very similar, doesn't it? This is a solid oxide fuel cell. It's the same device, but it's running in reverse, okay? And so this time, it's a reaction that wants to take place. We're taking oxygen and hydrogen and making water. That's a spontaneous process. So we can derive electricity from it. And this is great because there's no CO2 output if you use hydrogen as your fuel. Okay, so you put in a fuel, you put in some oxygen, you're operating this at high temperatures. These are all ceramic materials that make it happen. You're getting electrical power for your house, maybe for your truck, and the only byproduct is water. Okay, so it's clean. And this can be extraordinarily efficient. It can be 80% thermodynamically efficient. Okay, so we've got these different sandwich structure pieces in here, right? Looks like a sandwich. This middle part, which would be your peanut butter or your jelly, is called the electrolyte. This is a ceramic that is superionic. Okay? It's going to move ions through it really quickly, but not the electrons. Those have to go in the circuits. And what about the bread of the sandwich? Okay, we've got these two electrodes on either side. Those are also ceramics, but they have a special property that they move the ions through them quickly, but also electrons. And they help to catalyze reactions that have to take place in order to get this process to run. So I want to focus on this top piece of the sandwich, this top bread, the oxygen electrode. That's where the oxygen is coming in or going out, because this is the part of these devices that dominates the efficiency losses. And this is where all the attention is, not all the attention, a lot of the attention is in research right now. Okay, so this is a pie chart of all the different efficiency losses, where they're coming from. This takes the biggest part. So let's look at what the oxygen electrode is doing a bit more. Okay, so here's this piece of ceramic. It's going to act as the lungs of the device. It's breathing. Okay, it's going to take oxygen in from the air around it into the ceramic lattice. If you're running it in reverse, it's going to take oxygen from the ceramic and send it out to the air around it, very much like our lungs. Here's a zoom in of one of those processes. Okay, so here's oxygen coming from the gas, coming into a defect in the material, and then moving through the device. When this happens, it's like our lungs, right? If you pay attention to how you're breathing right now, you may notice your lungs are expanding, they're contracting, right? They're changing their size as you breathe. Well, ceramics are no different. They also change their size. Okay, and in this case, it's a little bit counterintuitive. When they lose oxygen, they get bigger. Okay? And this is a lattice expansion. We typically do not want this to be happening in our devices. If you think about ceramics, if you drop them, they break, right? They're brittle for the most part. They don't like to have materials expanding and contracting. It causes problems. So if we think about really trying to make new ceramics for this oxygen electrode, we want them to breathe quickly. That's going to help our efficiency. But we want them to not expand. How can we do that? So I just want to talk about very quickly a couple of snapshots from our research on this, answering those questions. So we're going to give a couple of vignettes on these ceramics that breathe. I want to talk about the ceramics that can breathe faster, and then the ceramics that don't change size when they breathe. And this is going to help the efficiency and the durability for these devices. So we'll start with efficiency. So when we want to study this breathing behavior in the lab, we want to work with very well-defined materials, very well-defined samples. And we want them, therefore, to have well-defined geometries. We want a good knowledge of the surface area where this is happening. And typically, we also want them to be very thin, so we're isolating that surface response where the breathing is happening. So in my lab, we do that by making very thin films, very thin layers of ceramics. So this is a couple of pictures from when we were setting up the lab. It is way more busy right now. We've got a lot more stuff in there. But this is what it looks like when it was clean and pristine. So this is one image. This big box here that's not even all in the picture, it takes up most of the room. This is a giant laser. And it's attached to this thing here, which is a vacuum chamber. So we take our giant laser. It's much, much more powerful, my laser pointer here, okay, because it's enormous. And we're going to fire it at a ceramic target, we call it. It's a pellet. It sits right here. We pulse the laser in, very high energy, and it makes this really pretty energetic plume of species. These kind of move upward, and they deposit up here on something called a substrate, and that's like a little square tile. Got pictures here, right? So here's the substrate, and the film is this colored region on it. And it makes these very, very, very thin films, nanometer-sized films that we can work with. How do we measure how quickly they breathe? Well, one way is these materials change color when they breathe. That's really convenient, right? So if they take in oxygen, they become darker. If they breathe out, they become more transparent. And we can track that under the conditions, the pretty extreme conditions, in which these materials are used. So what we do is we take our thin film, we put it in a furnace that heats it to high temperatures where these devices are being used. So temperature maybe 600 degrees C is pretty typical for us. And we're going to shine a light through it. And we're going to look at how much light comes through. And that's going to tell us what is the color and how much oxygen is in the material. And how do we change that? Well, we're also flowing gas through a transparent tube in our furnace. And we can switch that gas. Okay, so we can start with a very oxygen-rich gas and then go to an oxygen-poor gas. And the sample will respond to that. It's going to breathe out if you do that, if you step down the amount of oxygen. And we can follow how quickly it does that. Here's our step in our gas, okay? And we're going to follow the amount of light transmitted through the film over time. And by looking at how quickly this happens, we fit the data. We can figure out how quickly it's breathing. So that's great. We can do it for breathing oxygen in, breathing oxygen out. Okay. So I want to talk about how we've been designing faster breathing surfaces and faster breathing materials. Again, our goal is really fast oxygen exchange between the material and the gas. But there's problems. Usually these materials are made at high temperatures. Usually they're used at high temperatures. And under those conditions, the materials age. They have this issue of segregation of species to the surface, and it actually blocks that process from happening. It builds up a barrier on the surface. There's another problem about the expansion and the cracking that comes from that. I'll get to that later. But this segregation is a real problem. So what's our solution? Well, we're going to try to work at low temperatures instead. We're going to explore low temperature growth as a way to avoid this aging problem and low temperature use. So instead of a conventional oxygen electrode, we're going to explore these new low temperature electrodes, and this acronym here, MIEC, Mixed Ionic Electronic Conductor. Okay. So what do these look like? Okay, so we've been doing this low temperature processing of these materials. We grow thin films actually just at room temperature. It's quite convenient. And they're pretty boring when we grow them. They're like these uniform blobs. These are just images of slices through our samples. So they start pretty boring, but we take them through this process where we heat them just a little bit. Okay, just a very gentle heating. And as we do that, they transform into these really interesting nanostructures. And that's shown here. So they got lots of tiny little holes in them, lots of surface area, and they start to become ordered instead of disordered, which they start as. And these are pretty different from the normal kinds of high temperature electrodes, high temperature materials that people grow. Okay, so these are images, again, of slices through the material. And then these yellow or brown images are where we take a tiny little tip and we raster it across the surface, and we build up like a map of the topography of the surface. And so we can see that as well. And these side images are where we are using microscopy to look at the materials, what they look like. But it's not with normal light, right? The features that we're looking at here are so tiny. They're well below the wavelength of light. We couldn't use light to see them. we have to shine electrons through the materials to see them instead. So what do these new materials do in terms of their performance? Well, this is a measurement of how quickly they breathe. These are the conventional high temperature materials. And here's our new materials grown at low temperatures. They're at least 100 times faster at breathing oxygen. That's fantastic, right? They're so much better. Why does that happen? Okay. So one reason that we said at the beginning is we don't like the surface segregation that blocks the surface reaction. So maybe that's missing. And in fact, we can look at the surface chemistry. We can use a fancy technique called X-ray photoelectron spectroscopy. We're firing X-rays at our sample and looking at the electrons that come off, and it tells us about the chemistry right at the surface. And we can do that and get information about different depths down in the sample. So if we look at that, we see in the samples grown at high temperatures, they have this segregation problem. The element that comes out of these samples is strontium. And so that we have extra strontium at the surface. But our materials that are grown at low temperatures, they don't have that problem. So their surfaces are much better chemically. So that's great. But there's other reasons. There's other reasons for this good behavior as well. It's not just that the surface is nice and pristine. So one thing that we started to do was actually monitor the performance of the materials in pretty extreme high temperature conditions as we were making them undergo that transformation from the boring uniform films into these exciting nanostructures. One thing that we found was that they start to breathe when they start to transform and go from that amorphous, glassy state into those crystalline nanostructures. So this is the light that we shine through the sample. This is the temperature. These are the steps of the oxygen. So it doesn't respond to those steps until it transforms, and then it responds really quickly. So that's kind of cool. There's something special going on in the material that changes it from being inactive to active. The other thing that we did was we can measure the electrical conductivity of these materials in that same time frame. And what we saw is that they start pretty low, but they shoot up as we crystallize them, as we transform them. And so these materials are all of a sudden able to move electronic charge through them really quickly when this transformation happens. And so this is different from what's going on at the surface, but it's another reason for why they start to behave so well and they start to breathe really well. It's because this charge can move through and help that surface reaction. Let's see. So one way we also looked at that was we have a national lab in Illinois. It's pretty close by. Argonne National Lab. This is the image from above. So we can travel there a couple hours, take our materials, and look inside them with really, really high intensity light and understand the chemistry even better. And so we did this for these materials at different stages of that transformation. We did a whole time series. This is a different technique now called X-ray absorption spectroscopy. We're firing these high energy X-rays at our material and getting information about how they absorb them, about the local chemistry at the atomic scale in the materials. And it tells us how it's evolving, and it helps us to understand why charge is now moving really quickly through these materials. One of the reasons is that as oxygen comes in, as they crystallize, we're creating something called holes. And these are like positive version of electrons. Okay, they're charges, we're creating them in the material. And the other thing that we learn is from the structural changes, these are these atoms, and they're becoming better aligned during this process. And that helps these holes move through the material really, really quickly. So there's a couple things going on that help it. So the picture that we're getting is So with these new materials at low temperatures, the surface is pristine, it's great, the reaction is fast, but inside the material too, it's changing in all kinds of different length scales in ways that help the charge move through, and that also helps that oxygen breathing process. The other part of what we're looking at is the durability of these materials. I said they breathe and they change size like our lungs. Our lungs are not brittle ceramics, so they don't break. But ceramics are, and they can break, and that's not good. So this time we're going to work with bulk ceramics instead of thin films. We make them through these chemical approaches in the lab. So here's some pictures of the different stages getting into a ceramic bar. And the goal here is to minimize the size changes when they breathe. And again, the problems are that it causes these cracks and even parts in these sandwich structures to separate, and then the device doesn't work, right? Because these materials are expanding and distorting as they breathe. So I just show a couple of examples from our lab quickly. One of the new classes of materials that we've been looking at are these oxides that have a really kind of exotic element in. It's praseodymium, okay, PR. A couple of different compositions with that. And we've uncovered these compositions that exhibit almost no size change when they breathe. So how do we get to this? We have to measure really, really small size changes of the materials. And we also have to measure how their oxygen content changes. That's given by this Letta delta. So we plot the strain, the expansion or the contraction, versus how much they change oxygen. And we see that's almost flat. We do it at a bunch of different temperatures, almost no response. Fantastic. And we even compared this to everything that's been reported in all the scientific literature for this class of materials. So the property we care about here is the slope. This is something called a coefficient of chemical expansion. Fancy language just to say how much is it expanding or contracting as it breathes. Our materials have a much, much, much lower slope. These are record-breaking. They're about up to 500% less, than what's reported. So that's really cool. There's a lot of complicated reasons for why these work that I won't go into right now. But it has to do with where the charge is in the material. Another example is materials that breathe steam instead of oxygen. So the ceramics that do that for different devices. And here what we found is we can get this coefficient to be, again, about 500% smaller if we distort the structure. Okay, so you can have a structure that has really high symmetry. Everything is aligned and in place. And then you can have a structure that's similar, but everything is distorted and not really in a regular position in the same way. And these distorted structures are also materials that hardly change size when they breathe. Okay, so that's a very quick summary of that part. So, summarize with the efficiency side, this low temperature processing and the in situ crystallization gives really ultra fast oxygen exchange. And I think it's really promising for making these devices much more efficient, especially in the low temperature range. And then for durability, we're figuring out how to make ceramics that don't expand or contract a lot when they breathe. We can do that with low symmetry structures, and we can do that by changing how charge is distributed in the materials. Let me just close with this broader picture again of how ceramics are really important for sustainable energy technologies overall, right? And so, these technologies have to be able to convert between maybe renewable resources like sunlight, electrical power, chemistry, useful fuel, people in the environment. So we've got solar cells, we've got photoelectrochemical or solar thermochemical cells. Those make fuel using sunlight. We've got our solid oxide cells that I talked about tonight. That's just one piece of this big picture. We've got batteries up there, sensors, and ways of processing waste. So all of these are important in kind of a carbon neutral future. And ceramics are used in all of these, in different components in different ways, because they're stable in extreme conditions. They can transport ions or charge, they can catalyze reactions, and they can respond to their environments. So I think as we're looking ahead, all of these are areas of active research in materials science, and all of them play a really important role in building up this new sustainable infrastructure moving forward. So that's it. I just want to thank this is my group, right? These are my current students. These are my past students. And then all of the collaborators who helped with the work, right? We work not just with people at Illinois, but all around the world. And then, of course, it's funded by a lot of important agencies, so I want to thank them too, and I will finish there. Thank you.
All right. Excellent. Thank you, Dr. Perry. Folks, do you have questions for her after that talk? All right. People are stunned at how... What is your favorite element? Okay.
Great question. I think iron. Lots of reasons for that, right? It's super abundant, which is great. So that's one thing we care about a lot, ultimately, is working with abundant elements. So we're not having to mine in places where it might be harming the environment or causing other issues. So iron is abundant.
It's not ceramic because it's metallic, right?
By itself, but you can put it in ceramics, right? So all of those breathing studies that I showed, those had iron in them. And iron is the material that makes them change color. And it's the element in them that makes them catalyze those reactions and makes them able to breathe. And of course, it's important for life. So yeah, without hesitation, I will say iron.
Non-organic, non-metallic.
Yeah, so the iron is not by itself, right? It is mixed. So you have iron in there, but you also have oxygen, which is from that top right corner of the periodic table. You also have some titanium and strontium and other things in there. But iron is really the element that's doing the work. Does that make sense? Mm-hmm. Yep.
All right, let me head over here so that they can ask their question over the microphone.
Yeah.
Thanks for your patience.
Why does symmetry in the lattice increase decrease durability?
Decreases it. Yeah, so let me see if I can. Oops, I went too far. This one, yeah. Right, so the symmetric structures were giving really high coefficients, which means these materials, when they're symmetric, and they give oxygen out, or they take, in this case it's hydrating, so it's bringing water in. When they're symmetric, they do expand a lot when they bring in the water. Why that happens is actually something we're still looking at. We just hypothesized that this was the case. We tested it. We found that correlation exists. But right now we're doing some more in-depth studies, again at that atomistic level, to understand, in this case, where does the water go when it comes in? It actually splits. So you have an OH and an O, and they go into the defects, and they distort the lattice. And the way that happens with a symmetric structure appears to be different to the way it happens for this distorted structure. The way that the water gets accommodated in there, it goes into different sites, and it causes different atomistic distortions as it does that. So we have some insight into that from simulations that our collaborators have done, and what we're trying to do now is actually measure that experimentally. Yeah, great question.
Oh, let me pass it over here.
You said you were looking into the future. I was just wondering, how far into the future do you see any of this becoming more common?
Yeah, so it depends very much where in the world you are, I think. I spent a lot of time in Japan before I came here, and this is more a way of life there. They don't have the same natural resources, so there's been a bigger push to go to the hydrogen economy earlier. there. And so, you can go to hydrogen villages there where the whole neighborhood is using fuel cells and solar cells to power their houses and to heat their water. And they're building up an infrastructure of hydrogen fueling stations along their highways so that hydrogen-powered cars with fuel cells might be a reality. They're pretty expensive right now. I think the last time I checked the cost, it was something like $70,000 or $80,000 for a fuel cell car. So, it's going to take a while for that to be a reality. But these stationary fuel cells are already deployed across a ton of different scales. You can get portable ones to charge a laptop. Those are kind of expensive, but you can get bigger units all the way up to power plants. So they're used as backup power, they're used as main power. But I think in the US, it's taking a bit longer to trickle through. Yeah.
Any other, there we got another one.
Did you say that a large circular lab building was located in Champaign?
No, it's in the state of Illinois, but it's about 2-hour drive up in Lamont, Illinois. Yeah. So we go there when we can. Yeah. That's Argonne National Lab is the name of it.
Any other questions? All right, let's give Dr. Perry another round of applause.
Okay,
Thank you
thank
so
you all
much
for being
for
here.
coming out here and giving this wonderful talk. Really appreciate it.